What is a positive ion called? That would be a cation. Again, you can either remember it using the way that the T looks like a plus sign to mean positive, or that cats love to paw at things, so cation is positive. And then a positive ion has blank electrons or negative friends. The correct answer would be lost electrons. So when you lose negativity, you become more positive. Negative ions are called anions. Again, the an prefix meaning like kind of like anti, so opposite of positive, so it would be negative. And then a negative ion has gained electrons, so it has become more negative because it gained negativity. All right, very good on with that, everyone. Let's move on here. This is just a reminder to please to not share any personal information during class. Your participation is vital, and these sessions are always recorded for learning purposes. All right, congratulations to all of us. We've made it halfway through the week so far. We got 2 more days left. Remember, tomorrow is a recording day, and then we have one more lesson coming this Friday to finish off the week. All right. At the point now, we're going to start learning about nonpolar covalent bonds specifically. In general, as a sneak peek, a covalent bond is kind of like if you and a friend are passing a ball back and forth, right? Just playing catch like normal, right? Whereas an ionic bond that we learned yesterday is kind of like if one of your friends is a ball hog, like during like a game of soccer, and just keeps the ball for themselves, right? The ionic bonds, the ionic, the atoms are very greedy when it comes to ionic bonds. So, but we'll learn more about that a little later on. But specifically, we'll be able to explain how nonpolar covalent bonds are formed based off of electronegativity. So we will be reviewing that. And then we will learn how to draw Lewis dot structures for atoms, use Lewis dot diagrams to show how nonpolar covalent bonding forms, right? So we will connect all that together, and hopefully by the end, we should be pretty proficient with all of that. All right. I know, okay, good. So the links to the notes have just been posted. Either use the Larkin link or the Bang link, and please raise your hands when you have your notes open and you are ready to begin the lesson. Let's do a bit of a brainstorm. So please participate in the chat with this one. Let's talk about this first. Where are valence electrons located? Where are valence electrons located? People in the chat, where are valence electrons located? What does valence mean? Very good. Outer shell. Yeah, outermost shell. So we're talking about this shell right here, the outermost shell. All right, we're not talking about anything inside, we're just talking about the outermost shell. Now, how many valence electrons does oxygen have? Let's count them up. Look at the outermost shell that I circled around, and let's count those dots. All right, very good, there's 6. So 1, 2, 3, 4, 5, 6. Right, now, how many valence electrons do most atoms want? In our case, it'll be all, but how many valence electrons do atoms need to have? Think of the name. Exactly, it will be 8. So they want 8 valence electrons pretty much always. And what is this rule called? Think of the prefix that means 8, like oct, like octopus. If I have any Spider-Man fans in the chat, think of Dr. Octopus or Doc Ock. It is the octet rule. So let me type that out just really quick. It is the octet. I spelled it wrong, but we'll just leave it like that for now. And therefore, how many more electrons does oxygen want? So let's subtract. What is 8 minus 6? 8 minus 6. 2, exactly. Very nice, everyone. So it is 2. All right, so we're going to need this knowledge for lesson day, so let's move on. So we're just confirming, yes, valence electrons are in the outermost shell. Oxygen had 6, it wants 8. It's called the octet rule, and it wants 2 more. So important, just to mention, we learned yesterday that electrons don't just appear magically, they come from other atoms during bonding, right? That's how chemistry works. When we form a bond, either ionic like yesterday or covalently like today, that's called a chemical reaction. That's how chemistry works. All right, so let's just review electronegativity for a bit. So electronegativity, remember, is an atom's ability to attract electrons. So the more electronegative you are, the more greedy you are in terms of wanting more electrons. All right. If we look at the periodic table here, highlighted in pink on the upper right-hand corner is fluorine, which is the most electronegative element on the table. All right. So it's kind of like it's the most greedy element we have. Then on the opposite end of the spectrum, highlighted in yellow there, francium is the least electronegative and it tracks electrons very poorly. All right. Note that no gases are excluded from this because their valence shell is full, right? They already have the octet rule satisfied. Remember, all except for helium, but that's just because helium doesn't have enough shells to contain those 8 electrons. It just has the smallest innermost shell, but it still is happy with its 2 electrons, all right?
All right, so covalent bonds, when we talk about covalent bonds, we're talking about sharing, all right? So covalent means that things are always being shared. So we talked a little bit about ionic bonds yesterday. Ionic bonds involved ions in which we actually moved an electron from one place to another, resulting in ions, resulting in differently charged atoms. This time, though, they're not going to result in ions because that would be an ionic bond. Instead, they're just going to share their valence electrons. Now, this only occurs between 2 or more nonmetals. This is really important. Ionic bonds we learned yesterday occur between a metal and a nonmetal. Today, though, this type of bond only occurs between nonmetals. And the reason why is because the nonmetals are all kind of located in the same area, and therefore they all have very similar electronegativities, similar ability to steal electrons. So while they're much better at stealing electrons than our nonmetals, because the fact that they're all in the same place, that actually means compared to each other, they all have similar strength. Smiley faces emojis in the chat box if that makes sense. Because nonmetals are all in the same sort of area, they all have similar electronegativities. Even though they're all strong, they're all still similar to each other. So they have similar strength. So the result is you kind of end up in a tug of war between two strong atoms. And if you've ever been in a tug of war between two strong people, you will know that it's really hard for anyone to win the tug of war. So in this case, they end up just sharing the electrons rather than anybody outright winning the tug of war, winning the electrons. Covalent bonds are super important. They are found all throughout our body. For example, the proteins in your muscles and hair, the carbohydrates that give you short term energy, the lipids or fats in your body that give you long term energy, as well as your nucleic acids, which are your genetic material like your DNA that you got from your parents. These are all very complex and big molecules. And the cool thing about covalent bonds is they can make very complex and big molecules, which is a little bit different than ionic bonds, which tend to be simpler. So this is why covalent bonds are so important to you and me. We would not be alive without them. They're very important. This is number 2. Go ahead and fill in the blank with the word nonmetals. Only the word nonmetals. Make sure you spell it correctly. 20 seconds to raise your hand.
Okay, so let's learn a little bit about covalent bonding. So starting off simple with answering this part in the chat. A chlorine atom has blank valence electrons. So how many valence electrons does chlorine have? Remember, it's all on the outer shell. Excellent, Micah, Dima, Julia, very nice. Ronnie, don't hesitate to participate in the chat if you see other people answering. All right, so very nice. So yeah, chlorine has 7 valence electrons. So now it has 7, but it wants blank in total to be stable. What's always been that number that every atom wants to have? Exactly, it is 8 valence electrons. So we know it has 7 and it wants 8. So each chlorine shares 1 electron. We're going to describe how they bond. So we have 2 chlorine atoms that are both the same. They both have 7 valence electrons. And if they both give up that 1 valence electron to the other to share, then they will have both satisfy their octet in terms of sharing that extra electron that they really don't want, right? Or I suppose I'm talking in the opposite way. They want to gain one, but each of them can gain one to satisfy their octet. So the chlorine with the X's can give that one X over to the dots, and that chlorine atom with the dots can give that dot over to the X's. And then down below here, we can see that in the center, they're sharing those two electrons in the same shell, and thus that's how a bond is formed covalently. So each of them share that one electron and now appear to have full valence shells.
So I did want to mention, so if you now count up around this chlorine shell, how many electrons does it look like this chlorine now has? Go ahead and tell me in the chat. So if we ignore everything in the center and now count based on this new sharing, yeah, so now it feels like this chlorine on the left has 8, right? You can see 1, 2, 3, 4, 5, 6, and now it feels like it has an extra one in the middle, so 7, 8. Same thing with the chlorine on the right. If you look at its ring, now it feels like it has 8 valence electrons, and that makes it happy. Just a reminder that anytime things are bonding chemically, they are also chemically changing their properties. So chlorine by itself, a single atom by itself, is unstable and very reactive, whereas chlorine once bonded with another chlorine becomes Cl2, chlorine with two chlorines bonded together. And so now it does actually have unique properties. This is now a stable molecule that can actually exist on its own, unlike chlorine atoms do not want to exist on their own. Okay, let's go ahead and fill out number 3 and raise our hands. I'll go ahead and give you 30 seconds to fill that in. Capitalization does not matter, but spelling does. First blank is shares, second blank is unique.
Okay, so learning a bit more about covalent bonds, today we're specifically talking about the nonpolar variety of covalent bonds. So you might be asking yourself, well, what does nonpolar mean? So just in very simple terms, nonpolar means that it is not polar. Well, what does polar mean? Which we'll learn definitely more about tomorrow. But think of the Earth, right? How many poles does the Earth have, and what do we call them? The Earth has 2 poles, but what are they called? What names do we give them? It gives us like a reference for like direction, the North Pole, and then there's Santa comes from the North Pole, and then there's good job, the South Pole. So the reason why we call some covalent bonds polar and some aren't is because if we look at this diagram, the oxygen and the hydrogen atom are covalently bonded, but they're not sharing the electrons equally. Kind of like if you take out a compass and the needle point north, just like a magnetic pole, the needle is drawn more to the North Pole than it is the South Pole. That's why compasses work the way they do. So, however, if the electrons are shared equally in a nonpolar covalent bond, like these 2 carbon atoms, then we see that the kind of electron bubble around them is equally distributed evenly between both atoms. So if we were to kind of sever it in half and then like kind of like flip it around, then it would be symmetrical, all right? That's how we can tell that it is a nonpolar covalent bond. In terms of just recognizing which atoms do this or not, nonpolar variety will only occur when identical nonmetals like hydrogen or nitrogen form bonds with each other. So like we just described with chlorine, those 2 chlorine atoms would also be forming a nonpolar bond as well. All right, go ahead, give me a green check or an orange X if this is making sense. We'll be dealing with the polar variety tomorrow, but for now, just nonpolar. All right, very, very, very simple. Perfect. All right, so let's move on here. So for number 4 in our notes, let's go ahead and mark the words no and equally. No and equally. Just a reminder that capitalization when it comes to word answers does not matter. So don't let that throw you off. I'll set my timer for 20 seconds, and please raise your hand when you are ready to move on.
Okay, so just a reminder that again, when you're trying to think of this word of nonpolar covalent, words actually tell you what this type of bond is. So I know sometimes it gets overwhelming because you're like, oh, this is a lot of terms. I've learned about ionic, I've learned about nonpolar covalent, I'm going to learn about polar covalent, but the words actually tell you what this is. So what you can see here is you can see this prefix co here, and we're going to go over this again in just a moment to reinforce this, but the prefix co actually means to share. So when you see the word covalent, you should see the words co like sharing and valent like valence electrons. So they're sharing their valence electrons. So again, co means to share, which is different than ionic. Again, ionic, they're actually giving away an electron to create ions. And then nonpolar, again, polar, we talked about how our Earth has different poles, the North Pole and the South Pole. So if you think about nonpolar, that means that neither side is different, right? So nonpolar means neither side is different. And again, that comes from the fact that these are identical atoms, and so they have identical electronegativities. It's literally like twins, identical twins in a tug of war, and no one is going to win. So we end up with a bond that is equal on both sides, or you could even say symmetrical, looks the same on both sides. Go ahead and give me a smiley or an emoji if that helps to reinforce your understanding of this definition. Again, just by looking at the word has lots of hints for you. Amazing. All right, let's go ahead and move on here. So a good way to think about this, in case you're still having a hard time visualizing why this works, imagine you have two unhappy people. They're both cold here. We've got Emily and Sarah, and they only have one blanket between them. Instead of one person just taking that blanket, which in this case would be like taking the electrons, instead they're going to actually share them. So by sharing them, they both feel happy, even though they technically don't have their own blanket. So again, we saw that with that chlorine, once they started to share, they felt like they had 8 total electrons, even though technically they're definitely sharing them with each other. All right, go ahead and give me a green check, orange checks if that's beginning to make sense. Again, it's not technically their own electron, but by sharing, it makes them feel like they are full, feel like they are happy. Excellent. Okay, so let's go ahead and talk a little bit about other ways to remember this.
All right, so just a couple of fun tricks to remember the difference. When it comes to ionic bonds, if anyone is a James Bond fan out there, then they can remember the slogan, the name's Bond, ionic bond. I take my electrons taken, not shared, as if he wants his drink to be shaken, not stirred. And then, so you can remember it that way. And the reason is because between a metal and a nonmetal, the electrons are taken by the nonmetal, where the metal gives the electrons to the nonmetal, and electrons are transferred. All right, so electrons are transferred. And then with a covalent bond, remember co meaning to cooperate. Right? If you're cooperating with each other, then you're doing something together. And so this is happening between nonmetals only. And so electrons are being shared because you're doing things with each other, kind of like is depicted with the green chlorine atoms at the bottom of the slide. Right? And we also have a very suave ionic bond atom having his drink glass as one of his electrons. So very cool. So for number 5 in our notes, let's write the words transferred and shared. Transferred and shared for number 5. All right, go ahead. Please remember to raise your hand when you're ready to move on.
Okay, so we have this cool structure called the Lewis dot diagram or Lewis dot structure that actually makes it a lot easier for us to show what atoms look like as well as how atoms bond. So with the Lewis dot diagram, you actually only show the valence or outermost electrons. You'll have the symbol or the abbreviation for the atom in the center, and then you'll show the valence electrons on the outside. Now here's the deal: when you draw the valence electrons, you have to draw one per side. for each of the four sides of our symbol. And then you can start to repeat them. The reason why we have to do one per side and make sure there's at least one electron per side before we pair them up is because electrons in real life do not pair up immediately. Because electrons have like charges, they're both negatively charged, and we know that while opposites attract, likes repel. So like electrons are going to try to push each other away in order to fill up each of the four sides first before they're forced to pair up. All right, so that probably doesn't mean a lot to you. Let's go ahead and just do it because that'll make more sense. So fluorine is in group 17. And if it's in group 17, tell me in the chat, how many valence electrons does it have? Look at the last digit. Remember, group number is related to valence electrons. Number is related to valence electrons. Thank you. Yeah, that last digit is a 7, and so fluorine should have 7 valence electrons. Let's go ahead. I'm going to draw them out so we can see. I'm going to start with 1 on the top. Then again, go to the next side, the next side, and the next side. So again, I'm going to fill in each side with at least 1 valence electron first. And now I can repeat because now electrons will be forced to pair up even though normally they want to repel. So here's my 5th one, my 6th one, and my 7th one. So this is the most accurate or correct version of a Lewis dot diagram for fluorine. Smiley faces, emojis if you feel comfortable with this. We're going to practice this and then you will need to do one on your own. Okay, so again, make sure each side has at least 1 electron. Cool. So you can see that we have all of these different ways that we can draw these, and this is way simpler than trying to draw an entire Bohr diagram, because an entire Bohr diagram, you would have to include all the other shells, which is way too much work. Let's go ahead and practice one together. Which of these is the correct Lewis dot diagram for phosphorus? Taking a look here, phosphorus is in group 15. So that should help you remember how many valence electrons does it have. So you need to figure out which of these has the correct number of valence electrons. And don't forget the tricky part. You need to make sure that each side has at least 1 valence electron. Go ahead and circle that up on the board for me, or box it, or point to it, or do something. Get your answers up on the board. Make sure each side has at least 1 valence electron, and make sure it has the correct number in total. There we go. Perfect. Seeing lots of answers up there, seeing some corrections as well. That's okay. We can make mistakes just as long as we learn how to fix them. That's what's important. That's what learning really is. Excellent. All right, I see lots of people up there. I would totally agree here. So for sure, A does not work. A has 4. And we know that because phosphorus is in group 15, take a look at that last digit, it should have 5 valence electrons. So A does not work. C also does not work. It has 6 valence electrons. And while B does have 5 valence electrons, it's missing them on this side. Again, you have to have 1 at least on each side, so B also does not work. Great job on that one. This is the answer to number 6. Number 6, the only one that has the correct amount and the correct pairing is this one on the bottom right. Go ahead and take 20 seconds to answer that and raise your hands.
Instructing you guys on how this question works. It is multiple choice, so you have options A, B, C, and D. Your job is to choose the correct option for oxygen, which is just now circled right here. Keep in mind that you need to know both the correct amount of valence electrons, but also how they are spaced around the Lewis dot structure itself. All right, so go ahead, choose the correct answer. As always, if you need help, please use the Q&A chat and do not post any answers in the room chat. I'll give us about 30 seconds for this one. Let's work quickly.
Okay, so let's go ahead and talk a little bit about how we can actually use this in Lewis dot diagrams now. So Lewis dot diagrams can actually be used to also show bonding, and we can show electrons being equally shared in this. So for example, bromine is in group 17. So again, tell me in the chat, how many valence electrons should it have? How many valence electrons should it have? Yes, absolutely. It should have 7. So I'm going to go ahead and draw out the 7 valence electrons here. So we can see 1, 2, 3, 4, 5, 6, 7, and over here as well. 1, 2, 3, 4, 5, 6, and 7. Now then what we need to look for is we need to find unpaired electrons. So you can see here bromine has an unpaired electron right here, and this bromine has an unpaired electron right here as well, which makes sense. They're identical. Smiley faces emojis in the chat if you can see that. They both have 1 unpaired electron each. Cool. So now what we can go ahead and do is we can actually make them share with each other. So we can go ahead and say, you're going to share your electron over here, and you're going to share your electron over here. And now we're going to draw that as a single line between the bromines. All right, so I have bromine on one side. Sorry, let me just draw this out normally. So I have bromine over here on one side, bromine over here on the other side. And I'm going to go ahead and draw this as a single line between the two of them. Keep in mind that this actually does count as 2 electrons. All right, this does count as 2 electrons. So I'll go ahead and draw the other ones. Those other ones are still there. Those haven't changed. And now let's go ahead and take a look here, right? So bromine has 2 on the top here, 2 on the left here, 2 on the bottom here, and now it claims these 2 in the center that it's sharing. So 2 plus 2 plus 2 plus 2 gives me how many does this bromine on the left now feel like it has? How many does this bromine on the left now feel like it has? It feels like it has 8. So is it stable? Yes or no? Is it stable? Yes or no? Feels like 8, and yes, that is stable. And you would see the same thing with the other side, right? 2 on the top, 2 on the right, 2 on the bottom, and claiming these 2 in the center. That makes it feel like it has 8. Let's go ahead and take a look at sulfur. Sulfur's in group 16. How many valence electrons does sulfur have? Yes, it has 6, so let's go ahead and drop that up here. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and, oops, sorry. 5 and 6. And so this time each sulfur has 2 unpaired electrons, right? So each one has 2 unpaired electrons. And so those ones can actually end up being shared. So we're going to share this together as a single pair. And then we're going to go ahead and share these ones together as a single pair. And again, those will get drawn as individual lines. So let's go ahead and take a look here. We've got sulfur and sulfur. It gets 1 line on top, and that one counts as 2 electrons. And it gets 1 line on the bottom, and that one also counts as 2 electrons. And then don't forget these other ones stay the same. So we still have these other ones that stay the same. So again, counting up for sulfur on the left here, right? We've got 2 on the top. Oops, sorry. 2 on the top, 2 on the left, and this sulfur thinks it has all of these ones in the center. So these 2 right here and these 2 right here, 2 plus 2 plus 2 plus 2, this sulfur now feels like it has how many? Feels like it has how many? Again, it claims everything in the middle. Yeah, so it feels like it has 8, and so now it is stable. One more time, go ahead, give me green checks, orange X's as that's beginning to make sense. Once they share, each sulfur feels like it owns everything in the center, which actually makes it feel like it has more. This is the answer to number 8. Please go ahead and choose the diagram that shows 2 shared pairs. So 2 lines between the atoms. Go ahead and raise your hands. You have 20 seconds to get that done. Work quickly because we are out of time. I'm not going to go ahead and do nitrogen right now because we are out of time, but the last blank is that again, we draw pairs as single lines, but those single lines do still count as 2 electrons. So don't forget that when they share them, it counts as a pair, and a pair means 2. Each single line counts as 2 electrons paired together. This is number 9. Go ahead and fill in the blank. You have 20 seconds to fill that in with the word single.
Those dot structures and nonpolar covalent bonds. All right, if you haven't already, please turn in your notes if you are able to. And if you do not need to stay behind for anything, please move on to your next class. We will see you guys tomorrow. Have a great day.